Hi again. We're going to move into the material from chapter 12 from the textbook now, but we're also going to throw in a couple of elements from the previous chapters, actually chapter 11 and 12, and then move into 13. So it'll be a bit of a mix, hopefully very focused, and hopefully we'll all fit together with things you've either learned before or things that we're going to be needing as we go into the last few weeks of this semester. So the first topic is RC circuits. Now, RC will be very familiar to you. You've certainly seen the mechanical version of that scenario. And we've spent a lot of time discussing the similarities between resistance, between mechanical and electrical situations. We've discussed compliance and capacitance, and we'll talk a little bit more about the details of capacitors as devices. We've also had valves, which we said were the mechanical equivalents of diodes, or diodes are the electrical equivalents or analogs of valves. And so we've been fairly, I think, complete now in moving back and forth between these two domains. And this is a very powerful way to think about whichever one you may be having some trouble with or trying to understand better. So feel free to go back and forth between these two sets of analogs. You see them all here. There's one we didn't have a chance to talk about. It's called inertance, and it has inductance as its electrical analog. And we'll just have to leave that for another time. It's not that important in the body, as it turns out, nearly as much as capacitance is. So I think we should focus on that. So let's think a little bit about a capacitor. So I'm sure you have a vague notion about two plates and wires connecting them, and that's an accurate story. That's a very good view of it. You may also have heard of a thing called a dielectric, which is a very special material that slips in between the plates of the capacitor and increases its capacitance. The mechanics of how are not something we have a great deal of interest in probably, and certainly not time to get into. There's a key equation that describes this device, and again, this device, think of it mechanically as a device. Not a device, actually. Think of it as compliance, as a characteristic of, let's say, a blood vessel, and it captures its capacity to store blood. So when the pressure increases in a compliant vessel, the vessel gets larger and stores more blood. So the volume of the blood goes up. And we have these quantity analogs as well, and the analog electrical quantity to volume is charge. And so where a compliant vessel stores blood, a capacitor, or capacitance, but we think mostly in terms of capacitors as devices, a capacitor will store charge. And that's really its key features. It stores charge. And just like there's a relationship of compliance and pressure and volume, there's a similar relationship that exists in capacitors. So here the capacitor value, the capacitance of a capacitor, is equal to the ratio of charge over voltage. Remember, voltage is the same as our pressure. Or we can, of course, rewrite it, and you'll see it lots of different ways, as, for example, voltage is equal to the charge over the capacitance. And so there is this relationship, which we'll talk through in different scenarios, and hopefully you'll get a bit of intuition for it. Now, just like we were able to think about circuits with flow, resistance, capacitance, and pressures, and of course the volumes that go with those, we can think about very similar situations in the electrical domain. And we can think about charge building up on a capacitor just like volume built up on a vessel. And just like that volume that built up inside the vessel didn't leak and actually didn't even flow. The flow part of the Windkessel is what we capture in the resistance. But the compliance part is just blood that comes in and doesn't actually leave initially. So that blood doesn't pass through the wall. It just gets loaded up inside that segment of vessel. And charge works similarly on a capacitor. So charge enters the capacitor on one side or the other, depending on the polarity of whatever's charging it. And so the current flows and the current carries charge and the charge builds up on the capacitor. But fundamentally, a capacitor is also an insulator. We've talked about resistors and insulators, or conductors and insulators. And And a capacitor is a complete insulator, assuming it hasn't broken or been destroyed for some strange reason. But the goal of a capacitor is not to conduct, the goal is to store. And the question becomes then, well, how does current move in and out of a capacitor? What does it do? And it turns out that it enters, let's say positive charge enters, that charge that builds up an electric field, which pushes charge away, attracts opposite oriented charge to one side and pushes, let's say, positive charges away. So a device like a capacitor may look like current is flowing through it in the sense that we have charge coming in and hence a current coming in. That current loading up pushes current out the other side. And so from the outside it looks like there's current flowing, but those ions, if we're in biology, or those electrons, if we're in the electronics world, those electrons don't actually cross the gap. They don't cross the plates. They just build up on one side. And then, of course, as the external voltage changes, then that charge leaves the capacitor again. So the capacitor is this, sort of a strange device, but it has its parallels to compliance, or the compliance aspects of a vessel. Similarly to what we did with compliance and flow and volume, we can write down equations that capture the behavior of voltage and charge in a capacitor. So we have that original equation I mentioned before of voltage being the ratio of charge over capacitance. Now I can differentiate that equation in a very straightforward way. You've seen this in calculus before, and I get a dV dt. And on the right-hand side, I get 1 over capacitance, because capacitance it's not a function, it doesn't change with time. It's a constant in this equation, but charge is not. Charge obviously builds up and decreases and changes with time. So I can write 1 over c times the derivative with time of charge q, and I will get an expression that says dq dt. Now, if we think a little bit about the rate of change of charge, that's current. That's the definition of current. So we can rewrite this equation and say that dV dt equals current over capacitance. And that's the equation that we'll work with, just like we worked with the equations for pressure and volume and compliance in a mechanical system. And so volume, the derivative of volume with regard to time, is flow. And the electrical analog of flow, of fluid flow, is current, electric current. So we're in that sort of same domain that we were in before. It should feel somewhat familiar. And similarly, we can build very simple circuits that are like mechanical analogs, in which we have a capacitor which may have some charge on it already. That's its initial state, which is similar to the amount of pressure that a vessel has when we start connecting it to something. We can use a switch, just like we used a valve in the mechanical system, and we can connect another voltage to that capacitor, and we can watch the change in voltage as a function of time once we close the switch, just like we watched the rate of change or the time signal, the time changing pressure in a similar or analog situation that we had in the mechanical system. Now you're going to do this in the lab. The circuit that you'll be working with, you can see here, in which we don't just turn on a switch and watch things happen. We actually turn the switch on a positive value, and then we turn it to a negative value, and then we turn it back to a positive value. So we have a function generator that's going to apply alternating positive and negative voltages to that circuit. So through that resistor onto the capacitor, and then we measure through an oscilloscope, because we have time varying voltages on the capacitor, we're going to measure, or you're going to measure, changing voltage on that capacitor as a function of its resistance and capacitance. And that's going to, of course, lead to an RC type circuit, and very similar things to what you saw in the mechanical setting. In fact, the parallels are so strong that I'm showing you here the circuit and the slide and the derivation that we had a few weeks ago in the setting of a mechanical system. We were able to show that same process I just described, leading to a simple differential, first order differential equation with regard to pressure. In this case, we called it P1 in this simple circuit. And if you go back in your notes, you can find where we derived this. And we had an expression that depended on boundary conditions, initial conditions, and that led to a solution that we've seen and manipulated before, which is this exponential function that describes the pressure as a function of time parameterized or driven by the parameter of tau, and tau is the product of the resistance, the flow resistance, and the compliance of the vessel. Here's the slide for the electrical equivalent. And everything is in the same sort of place, just with analog or analogous values. So we even have a very similar schematic diagram, except we don't have pressure, we have, right, voltage. We don't have volume, we have charge. And we don't have flow, we have current. Exactly. So we can write down that same expression or similarly formulated expression for voltage as a function of time that we had for pressure as a function of time. And we can use that equation just like you did in the major project to describe voltage changes as a function of time in the setting of an RC circuit. So there's way more parallels than differences. And of course, because we have a solution that looks like that with the exponential to the minus t over tau, we also end up with a solution that also should look very familiar. This is the classic exponential decay, starting from an initial value, ending in a final value, has a time constant that again is 63% of the distance from the max to the min, like all that stuff that we've gone through in discussion sections in the mechanical setting. The same applies in electrical settings. We can just carry that knowledge over by just swapping variables and solve a lot of the same problems. And you'll be doing that in the lab. You'll be building a simple RC circuit, and then you'll be replicating your major project computer program, your Windkessel implementation. You'll be replicating that in the setting of actual components in an electronic circuit and be able to put together the pieces and show that you get the same behavior. And we'll spend some time talking about how to make that transition. There'll be separate information on that because you have values already of the compliance of your vessels or the cardiovascular system, right? We had compliance, we had resistance for each of those compartments. We have to change those from the mechanical or the hemodynamic variables of resistance and compliance into the electrical equivalence. And we can show how to do that because at the end of the day, the key thing is that our circuits have the same time constants. And that will be the key that allow us to go from one side to the other, is the product of those two have to be equal to the same time constants in order for the mechanical circuit that you implemented in the computer program to be the same as, or behave the same as, to be analogous to the electrical circuit that we're trying to build. And that's one of the steps that you'll be doing for the lab. And again, there'll be other videos that cover that.